Hello, everybody. So I'm going to talk about Parton densities in a series of lectures that I'm going to record here. This is going to be a very basic construction of the definition of a Parton density, operator definition of a Parton density. I'm going to focus on the unpolarized case. Now, I want to preface this by saying that the discussion I'm going to give is not entirely rigorous, but I think is much more intuitive than the more rigorous approaches that you could use. I would suggest that you do both, look at both derivations and compare them. So in our meetings, we've discussed the Parton model. We basically considered Feynman's idea that hadrons are clusters of essentially free particles, at least with regard to the collision that takes place in a process like deep inelastic scattering. And we come away from that with a very classical sort of intuition. So we're motivated, we come from this motivation to start thinking about hadrons as sort of clusters of nearly free particles. So that'll motivate the construction of a definition in quantum field theory for the number of particles like quarks inside of a state. We're going to work with an extremely idealized scenario. I want to imagine that we start with some cluster of particles, here represented by a bunch of blue dots. You can imagine them in a reference frame, and you should form this picture in your head of these particles just sitting there in the rest frame. And let's imagine that they're not interacting at all. There's no interaction whatsoever. It's not very realistic, but we'll take that as our starting point and build from there. Hopefully that is something we can translate into an approximation for something more complete. We start with a bunch of particles sitting there in the rest frame. In the Parton model, we basically looked at them in a highly boosted reference frame, where they're all moving sort of like this. So they're the target in some sort of collision. And once they're moving, they're all compressed. Okay, there's a Lorentz contraction, right? So these would all be in a kind of a Lorentz contracted pancake, right? And now in the moving frame, they're represented by lines showing the direction that they're going. They could be jostling around. But in the rest frame, they're just sitting there. They might be moving a little bit. Now, there's a very natural classical intuition that comes with this, right? This is essentially the Parton model intuition that we talked about last time. This is very easy to visualize, but now we want to characterize it in a language of quantum field theory. And since we're thinking of them as being at least almost free, let's start by assuming that they're exactly free. And we'll take this idealized scenario where we've got a cluster of particles that are sort of localized, like they would be in a proton or some hadron, but characterize them using operators from a free quantum field theory. And anyone who's taken the first semester of quantum field theory should have the tools to do that at this stage, right? You know how to construct states, you know how ladder operators, A dagger A, and all that sort of thing works. So we should be able to do that. So let me summarize the idealizations that we're imposing here. We're going to assume that this cluster of particles is literally free. They're all literally free. We're going to assume that they're fermions for now. We can do the same sort of steps for other types of field theories. We have, of course, in mind something like quarks, right? We're going to assume that there's only one type. Of course, for a real proton or hadron, there are up, down, top, bottom, etc. flavors of quarks, but let's assume that there's only one flavor so far. Now, this billiard ball picture that we had back here is very nice, but it presents some problems when we try to switch to quantum mechanics, right? Because if you're thinking about this in a billiard ball type way, you're thinking of all these particles as having some definite position and momentum. You're running a movie in your head, probably, of these particles jostling around. But of course, we know that if we go to quantum mechanics, then you can't have a particle with the position and a momentum specified at the same time. Now, where are we ultimately going is we want to construct or characterize quarks with particular momentum, right, in a parton density. That's what you're talking about. You're saying, how many partons of a particular specific momentum do I have? But now we know that if all the partons are localized in a bump, localized in some blob region like that, then they can't have definite momentum, right? So that's one of the things we'll have to address is how do we construct a momentum density using states that are localized in space. So of course, what we're ultimately going to have to do is take a state that characterizes the proton. I have a P in the bra vector here, that P stands for proton, but it could be any hadron. And schematically, it's going to be some kind of superposition of states of quarks with all different momenta, right? So there's going to be some wave function associated with that. Okay, so we're going to be dealing with relativistic states for the quarks that have specific momenta, but we need to combine them all together in some sort of wave function to create the state for the proton. So that's one of the other complications that we'll have to deal with this. I'm just listing the things that we're going to have to confront as we build up this parton density. So this is the essential question. What is the number density? And I'll call it f of k vector, f of k vector, to evoke the f that you usually see associated with parton densities in particle physics. The first question that I'm going to address is, how do we count the number of partons in any kind of state inside of some volume of momentum delta k vector? So this is a concrete task for us. Number of partons with some 3 momentum k vector. We only have to talk about 3 momenta here because these are free particles. So the 3 momentum fixes its energy. And we want to have we need an operator that counts the number of momentum eigenstates in a state like this. Right, so I'm just setting up what we're going to do over the next few pages. Now, one of the first things I want to do is review the way to translate between a Dirac field, which is going to be our quark field defined in coordinate space, and the momentum space creation and annihilation operators. Okay, this is getting back to what I just emphasized here. We ultimately want to work with a hadron state that has all the quarks localized in some region of space. So we want ultimately to, what we, as you'll see, we'll ultimately want to work with the coordinate space Dirac field operator. But we're going to be talking about counting the number of particles or the number of momentum states in momentum space, right? So we need the A dagger A, or in this case, actually, I've decided to use B as the notation for the creation or annihilation operator for the quark field. So B and B dagger will be the annihilation and creation operators for the quark field. So, by the way, note that I'm starting to label these equations. Okay, so fairly directly, be able to find that if I have a Dirac field in coordinate space, I should be able to translate it into a B with momentum k vector. So an annihilation operator for states with a 3 momentum k vector and spin s. Remember, this is a Dirac field. And that the translation goes like this. Okay, now this is the sort of thing I would normally leave as just an exercise. But the final form for the parton density does come with various pieces and elements that are maybe not entirely obvious. And so I think it's worthwhile to go slowly and check that each little piece of these kind of expressions we can understand. We can trace back to its origin in the first chapter of your quantum field theory textbooks, or the first few chapters at least. So a few of the things here come to mind. So first of all, it's basically a Fourier transform relation. So pieces related to that make sense. There's the integral over x, there's the Fourier exponential, and there's the field. But there are some things that are maybe not so obvious. For example, we've got this exponential here involving the energy k0. And since it's a Fourier transform in 3 momentum space, it might not be obvious why we need that. We've also got this gamma 0 sort of just sitting there. Why do we need that? Well, the way to check is to just substitute in the known expressions for psi, the Dirac field, expanded in terms of the creation and annihilation operators, and verify that we get back the B annihilation operator here. So let's actually just take a few minutes to do that together. And by the way, I switched my notation from Peschke and Schroeder, which is where I got these equations, Peschke and Schroeder 3.99 to 3.100. I'm using, for A, I'm using B, and for B, I'm using D, just because I derived this in a different context. So notations differ a little bit, and I'm going to have to use, well, I've got already a momentum K vector associated with this B, and my dummy momentum is going to be a K vector prime here. Okay, so let's go ahead and substitute psi in. And what you get is the second line here. So maybe what I can do is copy and paste this so we have it to refer to in the next slide. And all I've done is substitute this psi up into here in equation 1. And that's what I have in green down here to check. So everything is the same up until here, and then I substituted in this psi. You see the K vector prime, that's the dummy momentum that I'm integrating over. And I've got a sum over spins S prime. I need a dummy index for the spin of the quartz to sum over. Then I just need to work out what happens. So I'm going to use a few identities, maybe to review them, check Peschke and Schroeder, page 48, to simplify this expression. So let's blow this up and maybe look at the simplifications I've made on this first line here. So mostly what I've done is just combine things. So I've got the square root 2e k and the square root 2e k prime down here. I've pushed u bar s and combined it with the gamma 0 and the u s prime right here. I've still got the v k prime s prime. I've pushed this exponent and combined it with this exponent. That's right here. Okay. Still got the sum over s prime, still got the integral over k prime. Now, one thing that you might notice is that I've left off the prime on this k0 right here. And technically speaking, I shouldn't do that, but I'm anticipating that there's going to be a delta function at the end that's going to set k vector prime and k vector equal to one another. And so I know that k0 and k0 prime are going to ultimately be equal. And so these two exponents are just going to combine to give me a factor of 1. So now we see why we needed to include this factor. Okay, really the reason is that psi of x is a Heisenberg picture operator, right? The time evolution is included in the operator, whereas by convention, we always make the creation and annihilation operators in the Schrodinger picture. So we have to do a conversion between Heisenberg and Schrodinger pictures there. And that's the reason for that. And we see it coming out here. And okay, then we have relations like this and this. So what is U bar actually? It's a U dagger times gamma 0. Okay, and I want to use relations like this that involve a U dagger rather than a U bar. But now I've got a gamma 0 here. So when the gamma 0 inside the U bar hits the gamma 0 here, I just, again, get a factor of 1. And then I can make use of relations like this. Now, on the second term here, there's a similar kind of relation that when I sum over spins just gives me 0. And so I haven't written down a second term for this piece. I've just already taken it to be 0. Okay, so now looking at this line, we can see where the delta function comes in. If I integrate over x now, I get a delta function from this exponential factor that sets k vector prime equal to k vector, okay, times a factor of 2 pi cubed. And so when I take this integral over k vector prime, I just get a factor of 1, and I get back to this expression. Okay, and this expression is where I invoke this result, standard result from the textbook, that says when I sum over all of s's, I just get a factor of 2 times ek. Okay, now we see where this factor of 2 square root of ek times ek prime, you know, why we included that up here, because it cancels out the 2 ek that comes from this identity and leads us back to just v sub ks. Okay, so all I've done here is verify this expression. And excuse my sloppy switching of notation. Writing this, sometimes it's easier to write the s as a superscript than a subscript. So when I need to squeeze a bunch of stuff on the same line, I've done that. Okay. And by exactly the same type of reasoning, you can derive an expression for v dagger, the creation operator. Okay, so I'll leave that as an exercise for everybody. All right, those are going to be important later. I'm going to say, let's put them aside for now. I don't want you to forget about these relations, but I want to put them on the back burner and go back and look at the definition of a number operator, which is also something we should be able to construct just looking at the first few chapters of textbook like Pescher and Schroeder. So I want to return to the question that I posed at the outset of today's discussion. I want to ask the question, if I have some state, again, I'm labeling it by capital P in a bra vector, I want to ask how many of these, remember they're free B particles are in that state within some range delta K vector of 3 momentum. Okay. Delta K vector is a volume in momentum space and 3 momentum space. So I'm going to basically say what the answer is, and then we'll confirm that that's correct. So here, equation 3, I have got this operator n. By the way, I'm only going to be looking at the unpolarized case today. So states like this, let's assume that there's been an average over polarizations. Okay, here I have a number operator that is going to sum over the spins of the quarks, of the partons, these fermionic partons, and we integrate over some volume of K, three-dimensional volume of K vector, and hopefully it's plausible to you that this is the right thing, we put in a B dagger B inside the integrand. Okay, corresponding to K and the spin S. Okay, and let's imagine that we're just looking at some small volume of momentum space. So we're looking at how many quarks are in this small volume of momentum space. Okay, so now we need to check it. Okay, for the case of the vacuum, we should expect to find 0 quarks in the vacuum. And since B destroys the vacuum, that's a trivial case to check. Okay, more interesting is the case of a single particle wave function. Okay, remember these are eigenstates now that we're working with. We're going to go back to the coordinate space situation later. Let's look at a state of a single quark with a definite momentum K. Okay. And recall our relativistic normalization. So if you go back and look at the first chapters of quantum field theory, we need these square roots of 2 energy to get a good relativistic normalization for these states. And then the state is created from the action of a B dagger on the vacuum. So if my suggestion for a number operator, number of quarks with a particular momentum is correct, then when n operates on this single particle state, I should just get that state back because it should just be the number of particles times that state. The eigenvalue of capital N, this operator should be 1. Okay, so let's just check that that's the case. I'm going to take this, operate on it with n, and just substitute in the expression for n. I have to put some primes on the various things, right? So this already has a k on it, so let me put primes on the momentum, the dummy momentum that I integrate over, and primes on the dummy s that I sum over. And I have a structure that looks like this. And then all I have to do is refer back to the anti-commutation relations for the A's and B's, or in this case, the B's and D's, for the creation and annihilation operators for a Dirac field to see what I should do. So the anti-commutation just gives me 2 pi to the 3rd times the delta function that sets the 3 momenta equal to each other. These are the equal time anti-commutation relations. And a Kronecker delta that sets the spins equal to each other. Okay, and remember that I'm only integrating over a certain region. Of course, if I integrate outside that region, I'm going to get 0 from this because I'd be integrating outside the range of the delta function. So all I've done is copy and paste this down here. And when I apply anti-commutation relations to the bk prime, s prime, and b dagger ks, I get something with an annihilation operator on the right, so that destroys the vacuum and gives me a 0 result. And I get one of these delta functions that sets k prime equal to k. When I sum over s prime, that Kronecker delta function sets s prime equal to s, and I just get back the original state. So indeed, n operating on this state produces back the original state if k vector is inside that volume, produces 0 otherwise. Okay, so n actually counts the number of, well, in the case of 0 and 1, it's counting the number of quarks with momentum k and spin s inside the volume delta k vector. All right, so we've done this for 2 relatively trivial cases, the vacuum and the single particle case. Really, to use this, we need to verify that it's true in the general case, that n is doing this, counting the number of particles. So let's look at the general case. Now, to do the general case, I first want to derive a fairly simple identity that will make the derivation very slick and very quick. Okay, so I want to look at the commutator of the n operator with b dagger ks. And for simplicity, let's just assume that k vector for this page is inside the volume delta K vector, and see what this commutator is. Well, if I just apply the definition of a commutator, then I get this integral. Remember the definition of n that I've proposed. Maybe we should copy and paste it again from up here, right there. And all I've done is use this n with a b dagger k and s. Make sure to keep track of the primes that label dummy spins and momenta. And now I just, again, use several applications of the anti-commutation, the equal time anti-commutation relations for the B and the B dagger. So I'm going to use two applications of it here. Let's go through them. So the first one is going to be that I'm going to anti-commute these two B's. And of course I get negative with their order reversed, plus the delta functions that come from the anti-commutator. Okay, now if I look at the contribution from, I'm going to have two terms now, right? One from this part of the anti-commutation and one from this delta function. So let me look at what I get from here. I basically get back this term, but now with the order of the B's reversed in a minus sign, so just this right here. Okay, I'd like to do something else with that. And what I'm going to do is apply the anti-commutation again to these two pieces. Okay, that's what I mean by this blue brace, is to encompass what I get from this B dagger and this B dagger. Okay, they're both daggers, so they anti-commute. I can change their order and I get another minus sign. So basically, two applications of anti-commutation rules have given me two minus signs. I get back a plus, but now I've got a B, K, S dagger, B, K prime, S prime dagger, and a B, K prime, S prime. Okay, but that's just the same as this other term here. So those two terms now cancel out. And all I'm left with is the contribution from this delta function. Okay, so let me just write that. Now this integration simplifies to this once I've done this chain of anti-commutation relations. I've got a delta function. I integrate with respect to K prime vector, the three components of K prime vector. I've accounted for all the factors of 2 pi cubed. I've got a Kronecker delta function that sets S prime equal to S when I do the sum. And so I get back to B, K, S dagger. So this is the identity that I want. This commutation relationship just gives me back B, K, S dagger. Okay, so now let's use this to show the general case, in the general case, that n is indeed a number operator. It counts the number of quarks with momentum k and spin s in the target hadron. So we've already got the situation for 0 and 1 quark states. So that suggests that we should try to set up a inductive argument. Let's do that. Let's assume that we've got some state labeled by n. Okay, we're not going to put the spin and k every time because we need to have at least reasonably compact notation to explain this well. Okay, I'm abbreviating my notation here. I'm not going to put the k and the s every time because I want to simplify the notation and make this an easy derivation to follow, but the k's and the s should be understood to be carried along. Okay, let's assume that there exists one of these states that has n quarks with momentum k and s. such that when I operate with the number, the capital N operator, I get back N times that state. Okay, we've already constructed a state that has that property for some positive integer N. We know that it works for N equal to 1, right? We already checked that. So if we can show that, well, we'll just show it, that it works. We've already shown it for N equal to 1. Okay, so to go to the general case, let me again use this identity that we just derived up here and ask what happens when I operate with the creation operator on N. Okay, well, I know creation operator produces a state, so that will produce another quark in this state with momentum k and spin s. Okay, so we just add a 1 to the N. All right, these are the first chapter properties of the Dirac field Fock space that we're talking about here. Okay, but I already showed that bk dagger is equal to this commutator, so let's substitute in that commutator, apply the definition of the commutator here, and see what happens. Since I'm assuming this, then I know that when N operates on the little n vector, I just get back a lowercase n times the n vector. So that gives me this term right here. The other term is, well, I've just rewritten it here, capital N times bk dagger times the n vector, and I've put parentheses to highlight the different pieces of this expression. Now I can just add b dagger k, this expression, to both sides of that equation, and I get on the left side then bk dagger s n plus 1, because of this n, times the n vector, equal to this. So in other words, I get this expression. Okay, just from the previous line. So indeed, n acting on the n plus 1 vector gives back n plus 1 times the n plus 1 vector. Now, since I know this is true for the specific case of little n equal to 1, then I know now that it's true for little n equal to 2, which means that it's also true for little n equal to 3, and so forth. So this is now proven to be the general property of the capital N operator. So it does what we want it to do. If I've got some states with definite momentum for the quarks, for the partons, then the N operator counts the number of quarks with a momentum k vector. Okay, and since I've got this delta k up here, it's the number of quarks with momentum k vector inside that volume of momentum space delta k vector. Okay, so if we're trying to construct a number density, this is a useful thing to have for sure. Now let's consider how this integral that we've constructed, this object here, let's copy and paste that over here. Let's ask how this integral that we've constructed can be understood more generally. And let's do that by thinking about some kind of, well, I've called it a test function here, evoking something to do with distributions. But I have in mind just something, perhaps some sort of physical quantity x associated with each quark. So this would have units of x per quark. Then if I include that in an integral over some region of momentum, okay, then 3 momentum k, then this integral basically gives me the total x averaged over some number of quarks within a momentum volume delta K vector? Well, to see that, we can take delta K to be, say, infinitesimally small, and just think of this integral as, well, if delta K is infinitesimally small, it becomes basically some three-dimensional volume times this quantity, the ks dagger, bks, over 2 pi cubed t of k. Okay, and then this is just the number of quarks. This is then just the amount of x per quark. So we just got the total amount of x due to all the quarks within some momentum volume delta K vector. Okay, so from this, we see that this quantity inside the integrand here is nothing more than dn dk vector, d3k vector. This is a number density, meaning the density in momentum, 3 momentum volume. So number of quarks per unit of 3 momentum volume. That's exactly what we've been trying to build up here. Now, so far, we've just talked about the action of this density operator on exact momentum eigenstates, momentum eigenstates of quarks, right? But of course, what we're really interested in is the action of this density operator on an actual hadron made up of a bunch of quarks. Right? So what we really want is the expectation value. And if we're interested in, say, the proton, we want to look at the proton state or whatever hadron we're interested in. We want to look at that state. So again, let's say P, and we want to take the expectation value. I finally written down my first candidate, my first proposal for a definition of the parton density. Okay, it's the number of partons now inside of a particular hadron state per unit of 3 momentum K vector, or just substituting in my expression in terms of creation and annihilation operators, I get this. We have the 1 over 2 pi to the cubed that we have to carry along with us. And we're almost, well, this is a good definition. I mean, it is the number density, and it's inside of a proton. Now, it's not really useful or very useful yet. We're going to make it useful in the next lecture. And in fact, actually, let me change this definition a little bit. Let me cross out that first line. In anticipation for what I really want ahead, we want a definition ultimately that is density not in momentum, but in a momentum fraction. Okay, so in anticipation for that, I'm going to multiply by EP the energy of this incoming proton, this energy of the incoming hadron. Okay, and then it becomes, this operator becomes dn d3 k vector over EP. Okay, so I'm just going to now be able to say that the F1 is a function of k vector over EP. And it's the same as what I wrote on the first line, just now I'm carrying along this extra overall factor of EP, and that'll just turn out to be useful. Okay, before I end this discussion, note that I've put this subscript 1 here. That's because I'm going to make a few definition changes as we go along. And so to keep track of the definitions that we've been working with, I'm going to start labeling them with subscripts. So this is the first one, so I've labeled it with 1. Now, as I just said, this is fine as a definition, but it's not all that useful yet. And why is that? It's because these B dagger and B, well, we understand how they act if they're acting on momentum eigenstates, but the P has quarks inside of it that are not in momentum eigenstates, right? This is the point that I made right at the beginning of the discussion today. The P is some superposition of quark states with all different momenta, such that the hadron is localized in some region. So the next thing I really want to do is convert this into a definition with psi and psi bar, the coordinate space field operators. Why do I want to do that? Well, several reasons. One reason is that ultimately I want to derive Feynman rules for this kind of object. And I want to apply things that we learned in QFT class, like the Gelman-Low formula, the Wick's theorem, and all that stuff. And for that, I want to have something of the form time order operator, psi, psi bar, a bunch of fields. So I want to convert it into a structure like that. So that's the first thing I'll start on next time. And for now, I think I will stop.